Hi again, everyone. Welcome back. So this is going to be a lesson about matrix operations. And, what we've been doing lately is we've been learning about linear transformations, and then we learned that every linear transformation can be represented by its corresponding standard matrix. So at this point in the course, what we'd like to do over the next couple of sections is we'd like to learn how to do more with matrices. And now we understand that learning how to do more with matrices might help us with linear transformations because, they correspond with each other. So if you are following along with the same book that I'm following along with, this is section 2.1. So we're starting a new chapter, and the first section of a new chapter always has just some terminology and kind of getting established on what the chapter is going to be about. So I think that this section will be a little bit lighter. The main thing we need to do in this section is matrix times matrix multiplication, which we haven't really done in this course yet. We've done matrix times vector, but what if you have a rectangular matrix times a rectangular matrix? What does that mean? We haven't really done that yet. Okay, so let's go ahead and get started. All right, so matrix operations. As I was saying, the first section of a new topic usually has some terminology, and we have to start actually with some notation. So if we are given an M by N matrix A, and by the way, when we say an N by N matrix A, it might correspond with a linear transformation that we're currently interested in, but it could just be a matrix for the sake of being a matrix. Not every matrix question is going to be viewed as a linear transformation, even though it can be. Anyway, given a matrix A with a little ij, so the ij are a subscript, denotes the entry in the ith row and jth column. Example, if I had a matrix that was 2 by 3, we could think of its entries as being A11, A12, A13, A21, A22, A23. That's a useful way to quickly identify any entry in a matrix. And by the way, if this matrix was called capital B, I would probably use lowercase b ij for each of its entries. And so on and so on, if it was C or D or whatever. So we often use uppercase letters to represent a matrix, lowercase letters with subscripts to indicate the entries. We may abbreviate a matrix by A equals brackets Aij. Now that's a little interesting because this is an abbreviation. When you write it this way, it doesn't really tell you how big the matrix is, right? So it seems like this notation has limited usefulness. Really, we only use this notation if it's already clear what the size of the matrix is. Maybe if we're in a proof and we know we're dealing with, we've already said something about A being a general matrix or whatever, we might use an abbreviation in a proof maybe. So that's the notation I wanted to talk about. And now some terminology. First of all, diagonal entries. Diagonal entries are A11, A22, A33, etc. They form the main diagonal of A. So there's kind of two terms in this sentence, or I guess it's two sentences. Main diagonal, diagonal entries. Two sentences, two terms. A diagonal matrix is... What do you think a diagonal matrix is going to be? I mean, every matrix is a rectangular grid of numbers. You know, it could be a square, or it doesn't have to be a square. But you know, we can't really have a matrix that's a shape other than a rectangle. So what would a diagonal matrix be? It's going to be a square. In other words, n by n matrix. Whose non-diagonal entries are all 0. Wonder if you can think of a diagonal matrix that we've been talking about lately. I think it was in the previous video. The identity matrix, right? The identity matrix is an example of a diagonal matrix, because the identity matrix is always square. It has ones along the main diagonal, and everything else is 0. And the m by n 0 matrix. You know, we talked about the 0 vector. Well, the m by n 0 matrix has all entries 0 and is sometimes written as 0. It's funny, it's sometimes written as 0. This is not to be confused with the 0 vector. So we'll sometimes just write 0, and it would be like if we had a matrix, and then we said this matrix equals 0. What we mean by that is this m by n matrix equals the 0 matrix. You know, having all of its entries 0, and the size is usually clear from context. You know, if you already know that A is 2 by 3, and then you say A is equal to 0, you understand that it's the 2 by 3 0 matrix. Now, this section is called matrix operations. Let's talk about some matrix operations. First of all, sums and scalar multiples. These were discussed earlier in a previous lesson. See notes from... Let's see what this lesson was called. All right, this was in the video and lesson about vector equations. All right, so this was a while ago. We also talked about what it means for two matrices to be equal to each other. So we know what it means for two matrices to be equal, and we know how to add two matrices, and we know how to do a scalar multiple of two matrices. So I'm going to give you a little example to try here. Let's see. Okay. Example. Given the matrix A, which is 2, 3, 0, 5, and B, which is -1, 2, 4, -3, I'm going to ask you to find A plus B, and I'm going to ask you to find 5A minus B. So take a minute and try these. You could pause the video and give that a shot. Okay, so two parts to this problem. I guess we'll go ahead and do a plus b first. It's just good practice on adding two matrices. So I'm going to write them again, even though they're written above. We want to add these two matrices. And remember, all you do when you're adding matrices is you add the corresponding entries to each other. So, 2 plus -1 is 1. 3 plus 2 is 5. 0 plus 4 is 4. 5 plus -3 is 2. Not bad. And the next part, 5a minus b, let's do that. 5a minus b is going to be 5 times this matrix minus this matrix. Looks like we're going to be doing minus of some negative numbers. We'll be careful when we get to that. Let's deal with the 5 times a first. So 5 times a, that's a scalar multiple. It's saying take this matrix and scale everything up by 5. So it becomes 10, 15, 0, 25. And then we're still doing minus b. So just do corresponding entries. 10 minus -1 is 11. 15 minus 2 is 13. 0 minus 4 is -4. 25 minus -3 is 28. And that's the answer. So when you add or subtract two matrices, you just add or subtract the corresponding entries. You wind up with the resulting matrix is the same size as the matrices you started with. I'll give you another one. Let me give you one that's a 3x3 problem. In this problem, you're going to be given a equals 1, 0, 3, 4, -1, 5, -2, 6, 0. And I'm going to ask you to find 3i3 minus a. So take a minute and try this. Pause the video and give it a shot. Okay, I'm going to move this up, get rid of the old page. So 3i3, that's going to be, that's the identity matrix, right? The identity matrix could also just be called I. We could have just said 3i minus a here. If I had said 3i minus a, it would be clear from the context that we're talking about the 3x3 identity, because it would have to be the 3x3 identity in order to subtract a matrix of this size from it, right? It can't be the 2x2 or the 4x4 or anything like that, because then this problem wouldn't make sense. I put the 3 there to help you out, but I'm saying it didn't have to be there. Anyway, what's 3 times the identity matrix? That's going to be 3, 0, 0, 0, 3, 0, 0, 0, 3, and then subtract the given matrix from it. Three minus 1 is 2, 0 minus 0, 0 minus 3, 0 minus 4, 3 minus -1, 0 minus 5, 0 minus -2, 0 minus -2. So that's 2, 0 minus 6, and 3 minus 0. Let's just take a quick look, double check everything look okay there. Yeah, that looks good. All right, so I think that we're pretty comfortable with those types of problems. You know, adding two matrices, subtracting matrices from each other, scaling up like 3 times a matrix or 5 times a matrix. And of course, there's more to this section than just that. All right, first of all, let's get some properties out of the way. Some of these properties we might have said earlier in one of those earlier lessons, but I don't know if we've said all of them. So let A, B, and C be matrices of the same size. And let R and S be scalars. There's going to be 6 little properties here. Property A is that A plus B equals B plus A. Seems reasonable, right? Since we're just adding the corresponding entries, and we know that, well, this is called, this is being commutative, right? This is saying that matrix addition is commutative. And we know that addition of real numbers with each other is commutative. So when we add corresponding entries, that can be done in either order. So when we add matrices, it can be done in either order. Next property is when we have parentheses involved. This is called being associative. Basically says that the parentheses can be around the first part or around the second part. Property C says, I don't think we've said this one, A plus 0 equals A. So remember, we're not just adding the number 0. This means that we are adding the 0 matrix, and this would mean that we're adding the 0 matrix that is the same size as A. Part D is going to involve these scalars. R and S are just real numbers. So R times parentheses A plus B equals RA plus RB. It's saying that we can distribute the scalar across the parentheses. If we had parentheses R plus S times A, we can distribute in this sense also. We get RA plus SA. So part D and E are both about being distributive in slightly different ways. And part F says scalar R times parentheses SA is the same as parentheses RSA. So you can do the part in parentheses first on the left-hand side, SA, and then multiply it by R. Or you could just multiply the two scalars times each other, which is probably going to be considered simpler. Now, I think I have in my notes, I think we discussed these properties back in that lesson about vector equations. But back then, we only said these properties for vectors. And now we are saying these properties also hold true for matrices. A, B, and C are matrices, not just vectors. So if these look familiar, we did the vector version of it. And now we're being more general and saying not only do these properties work for vectors, these properties also work for matrices, which could be larger than just vectors. So I wasn't planning to prove these properties, but I'll tell you that if you were to write proofs, they basically would you'd basically write these matrices as columns of vectors. Like, you know how you can write a matrix as a list of its column vectors? And you would write it in that way and then apply the properties from vectors. You could say, oh, well, this property applies to vectors, therefore it applies to the columns of this matrix, and you'd wind up getting these properties. There might be other ways to prove it as well. All right, so now we can get to what I consider kind of the main topic of this section, and that is matrix multiplication. And in some ways, it's kind of surprising that we've gotten this far into the course without discussing this yet. So let me remind you, in an earlier video, let me see what this video was called. In an earlier lesson, so it was 1.4, the matrix equation. Ax equals b. We defined matrix vector multiplication. Matrix vector multiplication, meaning a matrix times a vector. And we defined it as A times X equals first column of A, second column of A, etc. You just think of it as it's columns, and then X is composed of, we'll say, n entries. So this is a rectangular matrix. This is just a column vector, and we defined it as you take the first entry of X times the first column of A, plus the second entry of X times the second column of A, etc., all the way up until you get to the last entry of X times the last column of A. Does that seem familiar, right? That's how we've been doing a matrix times a vector. And thinking of it in this format has been useful to us because we've talked about things in this class like linear combinations. We've talked about things like linear independence. So thinking of it in these terms, we see that all of these concepts are kind of related. But now we want to say, what about more generally a matrix times a matrix? And this is the part where I'm saying it's a little surprising that we haven't really talked about this. Just a general rectangular matrix times rectangular matrix. We've done scalar multiplication, but that's not the same. Scalar multiplication is like 3 times I or 5 times A. That's when you have a real number times a matrix. So matrix times matrix we need to talk about. Now, there's a couple of different ways to answer this question, actually. How do you multiply a matrix times a matrix? So, first of all, let's start with the definition. We'll have the definition way of doing things, and then we'll have another way of doing it. So, definition, let A be m by n, and let B be n by p. With columns B1, B2, etc., up to BP. All right, so B has P columns. Notice that B has n rows and A has n columns. The number of columns in A is the same as the number of rows in B. That's not just a coincidence. That's going to turn out to be a requirement. Anyway, then the product AB is AB. This is what we've wanted, a matrix times a matrix, and it is defined to be A times, we could think of it as A times B1, B2, all the way up to BP. So far, I haven't really said anything surprising yet, right? I've said that you take B, and all I've done is I've rewritten B as a list of all of its columns. But what we're going to say now is it's going to equal AB1, AB2, dot, 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 all the way up to ABP. Period. That is the definition of how to multiply a matrix A times a matrix B. So does this make sense? Let's see. A times B equals A times, this is just B written in a different way. And now this is the real new part. We're saying you take the matrix A times the first column of B, the matrix A times the second column of B, matrix A times the third column of B, etc., up until you get to the matrix A times the last column of B. So each one of these is a matrix times a vector. Matrix times vector, matrix times vector. And we know how to do matrix times vector. We wrote it up above. We do this for each one of those. So there are like sort of P problems here, right? And each of these P problems is one of these matrix times vector problems. And this will always work. So we're defining multiplication of two matrices based on multiplication of matrices and vectors, which we've already discussed. It's just that in this case, the vectors are the columns of B. All right, so that's the definition. We'll get to some examples soon. You know the thing I was saying about how the ends are the same? So let's emphasize that. Note, we must have, because you might say, well, what if they're not equal? What if it's m by n and p by q or something like that? Like, what if you had things that are not necessarily the same? So we must have the number of columns in A equal to the number of rows in B. These are the ends in the definition. So the definition already says this. This is already built into the definition. I'm just choosing to kind of emphasize it down here. What happens otherwise? What if they're not? Otherwise, AB is undefined. Period. All right, so that's maybe the new part is I'm telling you that AB we would just say is undefined or does not exist. Because in the definition, the ends are kind of built in that way. And we don't have a separate definition for this other case. We just say it's undefined. All right, let's do an example. I'll do this first example for us. Let's let A equal 2, 3, 0, 5, and B equal -1, 2, 4, -3. I think we might have seen these matrices earlier, but now I'm going to ask us a new question. I'm going to say find A, B. So I'll do this for us. And maybe one thing that I should address at this point before we go further, I want to tell you that there is going to be another way to multiply matrices. Right now, all we know is the definition that we said a few minutes ago, and that's what I'm going to use to solve this problem, and you'll see that the definition works. And then we'll talk about the other way. So if you've seen another way of multiplying matrices, trust me, we're going to get there, and it's going to be equivalent to what we're doing now. All right, but let's use the definition. By definition, of matrix times matrix. AB should equal AB1, AB2. Well, B only has 2 columns, so that's it. It's going to be AB1 and AB2. And I'll say off to the side that B1 represents the first column of B, and B2 represents the second column of B. I guess we could do a quick check. Is the number of columns in A equal to the number of rows in B? Maybe I should have done that first. Yes, the number of columns in A is equal to the number of rows in B, so this is going to be defined. We need to find these two things, right? If we find this and we find this, then we've answered the question. So let's find AB1 first. AB1 is, here's A, and here's B1. Matrix times a vector. And I'm going to do this according to how we do matrix times vector. Like we said earlier, we take the first entry of the vector times the first column of the matrix plus the next entry of the vector times the next column of the matrix. We would keep doing that until we get to the end. We're already at the end. What is this going to be? This is going to give us a little column vector, right? So -2, 0 plus 12, 20 equals, I guess we get 10, 20. That's half of the answer, because the total answer we're looking for is going to have AB1 and AB2. We just found AB1. So now let's do the same thing for AB2. So AB2, it has the same A, 2305. Just B2 is 2, -3. Okay, so first entry of the column vector times first column of A plus, we're going to do plus -3, right? Instead of writing plus -3, I'm just going to write -3. Let's just do that. Plus -3. All right, and then this is going to be 4, 0. I think we can just say -9, 15. And we wind up with 4 minus 9 is -5. 0 minus 15 is -15. But let's just make sure that we write our finished answer to this question. Did we find AB? AB is supposed to be this matrix. It has this column and it has this column. We found the columns separately, but for our final answer, we should put them together. And we found 10, 20 is the first column, -5, -15 is the second column. And that's the answer. So it was just like 2 problems in one, 2 matrix times vector problems. So we did a 2x2 matrix times another 2x2 matrix. And the result was a new 2x2 matrix. Notice, yeah, you know, we haven't really said this, but maybe it bears mentioning this, like, note, to multiply A times B, we do not just multiply corresponding entries. I put an exclamation point at the end of that. And you might say, why not? And I would say, because that's not how it's defined. We had a definition for the product AB, and it told us to do this. Well, I don't know if that's a very satisfying answer, but I guess I would say that matrix multiplication is defined in this particular way because it's going to be very useful for linear algebra to have it defined in this way. Might not really be clear yet, but hopefully it will be soon. That we define matrix multiplication in this funny way because this is what's useful. Multiplying corresponding entries, that could be considered like a completely separate operation with a different name. And it turns out that that is not very useful for applications or anything. Okay, complete side note. I'm not even going to write this, but multiplying corresponding entries is sometimes known as the Hadamard product. I'm not going to quiz you on that. You're never going to see it in this class. And I'll tell you that I didn't actually see any uses of the Hadamard product until I was in grad school. And it's just very rarely used. So it typically would have a different symbol in between A and B. So it's a different kind of product. When we talk about matrix times a matrix, this is the type of product that we mean. We mean going through this whole process. So I think I said something a few minutes ago about how there is also another way to multiply two matrices, and it's going to turn out to be equivalent to this. So let's explain it in words first, and then we'll do an example. So this next way that I show you of multiplying matrices is going to be the method that we use more often, and it's called the row-column rule. The row-column rule for multiplying matrices. So first of all, suppose A is m by n, and B is n by p. Then AB equals C, where, so matrix times a matrix equals a new matrix, where each entry of C is. It seems like we could be able to define matrix multiplication in this kind of way. Like, can we just find a formula for each entry of the result? The result is the matrix C. Could we just get a formula for each entry? So I could say each entry of C, we could abbreviate as Cij to make sure that we're talking about the ith, what do I want to say here? The ith row and the jth column. All right, so this is a lowercase c. It equals A I1 B1J plus A I2 B2J plus, do you see a pattern here? A I1 B1J, A I2 B2J. So the ones go together, the twos go together, plus dot dot dot, all the way up to, well, how far do we need to go? You notice that both of these had AI something, B something J, AI something, B something J. So this is going to be AI something, B something J. We have to go all the way up to N. That's how many of them there are. And I'll just say note, C will be, did we talk about what's the size of the resulting matrix? In the example that we did up above, we did a 2 by 2 multiplied by another 2 by 2, and the result was 2 by 2. I'm going to tell you the result is m by p. So let me show you some things here before we go any further. I'm explaining this rule in words. It's going to be a lot clearer once we do an actual example. But a couple of things to notice just about what we've written here. First of all, I'm going to underline this lowercase n and this lowercase n. And I just want to remind you that these two little n's that I underlined, they have to be equal. Up above, we said that they have to be equal or the whole thing is just undefined. Okay? What are the other letters that are here? There's an M and there's a P. Well, those two, they tell you what size C is going to be. So when you have a size of A and a size of B, you make sure that the ends are the same, and then the other two tell you the size of the product. So if you had a 2 by 2 matrix and another 2 by 2 matrix, the result would be 2 by 2. But it could get more interesting when you have other shapes and sizes, when you've got things that are not just square. All right, so this means the entry of C in row I, column J, is computed using what parts of A did we use and what parts of B did we use to compute Cij? Maybe we could just focus on what parts of A did we use. We used AI1, AI2, AI3, AI4, AI5, all the way up to AIN. I'm going to say that AI1, AI2, etc. means we are using the ith row of A. Because what's the ith row of A? It's AI1, AI2, AI3, etc. What entries of B did we use? We used B1J, B2J, B3J, B4J. That is the jth column of B. Okay, let's do an actual example. I'm going to get this started for us. I know it probably sounds confusing when it's written out in words like this. So let's see an example with actual numbers in it. So let's say we are given A equals 1, 2, 3, 4. It's a 2 by 2 matrix. And B equals 1, 3, 5, 4, 0, 1. I'll get us started on this. Maybe I'll ask you to finish it towards the end. We're going to find A, B. All right, before we do anything, let's make sure the sizes match up. Let's make sure that the sizes are compatible with each other and that this is actually going to be defined. Otherwise, if we find that the sizes don't match up correctly, we could just say undefined, does not exist. And then that would be, we'd be done. All right, we want to do this matrix times this matrix. All right, allegedly we're trying to do this. Let's check the sizes. What is this? This first one is a 2 by 2 matrix. I'm going to write that underneath it. The next one is 2 by 3, because remember, we say the number of rows first and the number of columns second. So we say this is a 2 by 3 matrix. I'm going to underline that this 2 and this 2, you don't have to underline it. This is kind of scratch work. But I'm pointing out to you that this 2 and this 2, they are equal. That checks out. Because these two are equal, it means that this product does exist. Furthermore, I know what size the product is going to be. The result is going to be 2 by 3. It's the other numbers, the 2 from this and the 3 from this. So I know that my answer is going to be 2 by 3. So do I know what the entries are? At this point, I don't know what the 6 entries are, but I know that there's 6 of them because I know it's 2 by 3. So I'm just going to call them C11, C12, C13, C21, C22, C23. If I could find those 6 numbers, then we'd be done. And I can find those 6 numbers using the row column rule. So I need to move this page off the screen, so I'll just point to it one last time. We're going to use this row column rule to find each of these 6 things. So we're kind of turning this problem into 6 smaller problems. How to find C11, C12, etc. Okay, let's get started. You could say we already got started. We at least kind of set up the problem. All right, to find C11. I said that the last thing I said on the previous page was I said the entry of C in row I, column J is computed using the ith row of A and the jth column of B. So I want to use the first row of A and the first, wait, here's the first row of A. And the first column of B. Right? That sentence that I put at the last sentence before this example started. It said that to do this, we use row 1 from A, column 1 from B. How do we use them? The row column rule says, you could do it by the row column rule, like as it's spelled out up above, but I'm just going to point to these numbers and show you. We take the first entry from this times the first entry from this. So 1 times 1 plus. We take the second entry from this times the second entry from this. 2 times 4. And then we see, what does this equal? Equals 9. I'm going to circle that. That's part of the answer. We just found C11. So in the end, we're going to put a 9 there. See, so we're making 6 little problems out of this, but they're going to be pretty small. Let's move on and find C12. To find C12, we want to use row 1 from A and column 2 from B. Sometimes I see people will circle the appropriate row and column that they're using. So you could look at A and you could circle row 1, and then you could look at B and you could circle column 2. And if you did that, some elongated circles, you could kind of imagine that those 2 circles kind of intersect right here at C12, which is what we're trying to find. I don't want to circle them because then we have 6 of these things to do, and we're going to wind up with a mess of lots of circles. Anyway, 1 times 3 plus 2 times 0. You see where those numbers came from? The 1 and the 2 came from A, and the 3 and the 0 came from B. So this gets us 3, and that's going to be C12. Now, I'll tell you that as we do more of these, you don't have to necessarily write out quite as much as I'm writing. I'm writing this much because it's new to us. Unless you may have seen it in some kind of pre-calculus class or something like that. We sometimes cover it. You use 1, 2, and column 3 from B is 5, 1. So 1 times 5 plus 2 times 1 is 7. I think the hardest thing about this is just to watch out for little mistakes. Watch out for like copying the wrong number or making like a little arithmetic mistake. All right. We found actually 937 is going to be the top row of our answer. So we're halfway there. But we need to find the next row. So we need to find like C21. So for C21, now this is the first time we finally need to use the second row of A. So every row and every column of both A and B get used. Right now I'm using row 2 of A, column 1 of B. 3 times 1 plus 4 times 4. That's 3 plus 16 is 19. All right. I'm circling these, but in the end, we have one big answer that we'll circle. It's going to be a 2 by 3 matrix. It's going to go 9, 3, 7, 19, something, something. And that is going to be our answer. How about this? I'd like you to try to finish it from here. So maybe pause the video and see if you can find the 2 remaining entries. All right, so for this problem, I'm going to continue writing it the way that I've been writing it. And, you know, you'll see that in future problems that we do, we're not going to write out quite as much detail. But hopefully this was useful to understand the overall process of which numbers match up with which numbers. So you should have gotten a 9 here. And then to find C23, we use row 2 from A, column 3 from B. You could actually check that we did wind up using every combination, right? We used every combination of a row from A and a column from B. 3 times 5 plus 4 times 1 is 19. Hey, we got a 19 for one of the other entries too. That's just a coincidence. So the final answer then, let's put this all together, that AB gets us the matrix 9, 3, 7, 19, 9, 19. And you should write final answer like that. Put them all together. Yeah, it's just a coincidence that 2 of them were 19. So I want to do another one now to show you how we can do this without writing so much. This is the method that we like to use to multiply 2 matrices, but it's a lot of writing. So let's how about I do this next one? I am going to find, I'm just going to make it a 2 by 2 problem. Usually in linear algebra, if we say something is a 2 by 2 problem, it usually means everything in the problem is 2 by 2. Okay, I'll do this one without writing so much. I'm going to say that this equals, all right, in my head, without writing so much, I'm going to quickly do a check and make sure it's defined. This is 2 by 2, this is 2 by 2. So the 2's that are supposed to match up, they match up with each other. And the resulting matrix I'm expecting to be 2 by 2. So in what I write here, I'm expecting to have 4 entries. The first entry in the upper left is going to need to use row 1 of the first matrix, column 1 of the second matrix. So I'm looking at the 2, 3, and the 1, 0. The 2, 3, and the 1, 0. How do they get combined with each other? It's going to be the 2 times 1 plus 3 times 0. Let's just write that. 2 times 1 plus 3 times 0. Let's just leave it like that for now. Let's move on to the upper right entry of this matrix. Okay, that's still in row 1, so it needs to use row 1 of A, but now it needs to use column 2 of B. So 2 times 2 plus 3 times 1. Let's write that. 2 times 2 plus 3 times 1. I know that I drew this and it looks kind of elongated like a long rectangle, but this is going to be a square. It's okay if you make it look, it doesn't have to geometrically look like a square. It could still be 2 by 2. All right, lower left corner. We're in row 2 now, so we need to use the 4, 5 row from the first matrix. 4, 5, and I need to use the 1, 0. 4, 5, and 1, 0. So 4 times 1 plus 5 times 0 is what goes here. The last entry, it needs to use the last row of A and the last column of B. So the 4, 5, and the 2, 1. 4 times 2 plus 5 times 1. See how I found which numbers I needed to use without writing half of a page? And now we just have 4 little arithmetic problems to simplify. Okay, what is 2 times 1 plus 3 times 0? It's 2. What is 2 times 2 plus 3 times 1? It's 7, etc. This is going to be 4. And then this last one looks like it's 8 plus 5, so 13. And we just did a matrix times a matrix. And this is usually about how much work I would write on a piece of paper. I think writing this thing here helped us match up all the numbers. I wouldn't really try to go straight to the answer doing it all in my head. I would write this kind of, this amount of work. So I'm going to have an example for you to try, but before we do that, just a couple of quick things. I want to say that if you want to write more, that's perfectly fine with me. So some of you may have seen this in a previous class, some of you might not. So if this is new to you, write as much scratch work as you need. That's perfectly fine. I want to tell you that what I just did is equivalent to what we did in the previous problem, breaking it down into all of this. It's the same thing, right? I also want to tell you that what we've been doing in these 2 problems is equivalent to this problem that we did. Remember when earlier when we had the actual definition of matrix times matrix, and we said you do this, you do like AB1, AB2, and you do AB1 and you find a column, AB2 and you find a column, and then you put them together. It is equivalent to what we've been doing here, and you can check that. You can do the problem both ways if you want, and you'll see that you do get the same answer. That's what makes the row column rule valid. That's why it's okay to use the row column rule. It gets you the same thing as the definition. All right, let me give you a problem to try. Get a fresh sheet of paper for this. All right, let's say you're given A equals 1, 3, 0, 4. There's going to be multiple parts to this, so wait until I write all of it. We're not just multiplying. There's 3 parts. Given A and B, part A, find AB. Part B, find BA. And part C, does AB equal BA? All right, so I'd like you to pause the video, take a couple of minutes, and try to do these 3 parts. Okay, so let's answer this. So kind of interesting that this is even asking us, does AB equal BA? If you've never seen matrix multiplication before, then that might seem like a surprising question. Like, why wouldn't they be equal? Well, we're going to find out. We're going to do it and find out if they're equal. So AB equals this matrix times this matrix. They're all the way up there, you know, 2 or 3 inches away, and I'm thinking, I don't want to have to look all the way up at the top of the page when I have to match up rows and columns. I prefer sometimes to just rewrite them side by side. And that helps me sometimes to see which row and which column go together instead of having them like all the way. Or like if you were taking a quiz or a test and you had matrices on some, you know, some test paper, and then you're working on scrap paper and you have to go back and forth between the 2 pages, just rewrite them side by side. I think it helps. This helps me see that I need to do 1 times 2 plus 3 times 4. I need to do 1 times 5 plus 3 times 1. See where the 1, 5, and 3, 1 came from? I need to do 0 times 2 plus 4 times 4. I need to do 0 times 5 plus 4 times 1. And let's do these 4 little arithmetic problems. That's 2 plus 12 is 14. 5 plus 3 is 8. And so on. You get 16 and you get 4. So we found AB. That's the answer to part A. Part B wants us to do BA. So I'm going to write B. And then I'm going to write A. And here I think it's especially useful to rewrite the 2 matrices side by side in the correct order that this problem wants. It wants B first and then A. I think if I were looking up here at this B and this A and they're in the other order, I would get lost and I would maybe copy the wrong row or the wrong column. But when I put them side by side in the correct order, it helps. So we need to do 2 times 1 plus 5 times 0. Over here, I need to do 2 times 3 plus 5 times 4. Over here, I need to do 4 times 1 plus 1 times 0. And here, I need to do 4 times 3 plus 1 times 4. And then I need to see what does it give us as a result. 2 plus 0 is 2. Oh, look at that. You can already tell. You can already tell what the answer to part C is. You can already tell that these matrices are not the same. We got a 2 in the upper left, so it's not a 14. Let's keep going. This is going to be 6 plus 20 is 26. This is 4 plus 0 is 4. And this is 12 plus 4, which is 16. And that's the answer to part B. So the answer to part C, it just said, does AB equal BA? Well, look at what we found for AB. Look at what we found for BA. No, they are not equal. Not even close. They're not even close to being equal. Like, they don't have any of the same entries. So, I guess we just learned something. We learned that AB, it seems like it's not necessarily equal to BA, that they could be totally different. Is there something about these matrices that made that happen? Like, are these special matrices that I handpicked to get this result? Is it going to sometimes, would AB and BA sometimes equal each other, but not for this problem? All right, so I'm going to give you this as a warning. In general, AB does not equal BA. I'm going to say there are rare exceptions to this. When I say rare, maybe I should explain. What do I mean by rare? Okay. There's infinitely many matrix multiplication problems that you could come up with. Come up with a random matrix times another random matrix, right? There's infinitely many problems. There are also infinitely many exceptions to this rule, okay? But these are relatively rare. Relatively rare. If I gave you 100 problems, I would expect AB to not equal BA in all of them, unless I purposely designed a problem to get them to equal each other. That's how rare it is. Okay. So we say that matrix multiplication is not commutative. Commutative. Remember, like we said, A plus B equals B plus A. So matrix addition is commutative, meaning you can add two matrices in either order and still get the same result. Matrix multiplication. This is actually one of the famous examples of an operation in math that is not commutative. Because so much of the stuff you see in math, like addition of real numbers, multiplication of real numbers, I feel like a lot of things are commutative. This is not. Can you think of another example of something that's not commutative, just in math in general? How about subtraction of real numbers? You know, like 4 minus 1 is not the same thing as 1 minus 4. So I guess that's another that's another simple example of something that's not commutative. Anyway, all right, let's get some properties. So being commutative is not a property of matrix multiplication. But what about the other types of properties? What about associative? What about being distributive? What about other things? So I have a list of, how many here? I think I have 5 properties to tell you involving matrix multiplication. So let A be m by n, and let B and C have sizes such that the following sums and products are defined. We're kind of saying that in a general way so that we can say 5 different rules, and just we're saying that A, B, and C are going to be sized appropriately so that all of these do exist. First property, A times BC does equal parentheses AB times C. All right, so this is the associative law. Associative law for matrix multiplication. Next one is, what if you have A times B plus C? This does equal AB plus AC. What do you think this is called? Some kind of, we're distributing, right? So should we call this the distributive? We call this the left distributive law for matrix multiplication. That seems to imply that there's also going to be a right distributive, and there is. B plus C times A. This equals BA plus BA plus CA. And this is called the right distributive law. And the order that we're writing these things in, like this has to be BA, not AB. The order matters. All right, and I said there were 5 of these. We are on the 4th one. This is going to say R. Oh, I didn't even say what R is. Well, we'll say it afterwards. It's going to be a scalar. RAB equals RA times B, and that also equals A times RB. We're saying that the scalar, I don't know if this one necessarily has a name, but that this is true for any scalar R. We're saying that the scalar can be moved around. The scalar can be out front. I guess in the first way we wrote it, it's suggesting that you do the part in parentheses first, right? So you do the matrix multiplication first and then multiply by the scalar. In the second way we wrote it, it's saying do the part in parentheses first. So multiply the scalar times the first matrix, then multiply matrices. And in the third way, we're saying you could even move the scalar over to here, and the parentheses suggest that you do the part in parentheses first. So you do the scalar times the second matrix, and then you perform this matrix multiplication. One thing that's important is you're not multiplying R times A and R times B. You're either multiplying it times A, you're multiplying it times B, or you're just multiplying it times the product after the product is taken. Okay, and then one more rule. I M A, that's the identity matrix, right? That's the M by M identity matrix. I could leave the little m off and I could just say, you know, size is clear from context. Technically that would be okay. M by M, just to show you that this product is defined. That's M by M. It's being multiplied by something that's M by N. So yes, it seems like it checks out. This actually equals A. The identity matrix times A just equals A. Something that I want you to think about is this is kind of why it's called the identity matrix. It's because when you multiply it times A, you just get itself. So it's a multiplicative identity. So it's kind of like multiplying by 1. Also, this is equal to A times I, but then it would have to be the N by N version in order for the sizes to match up. All right, and this is the identity, multiplicative identity, I guess you could say, for matrix multiplication. Oh, here's a question. If that's a multiplicative identity, is there also an additive identity? Yes, we already said it earlier. A plus 0 equals A. So adding 0 doesn't change a matrix. Multiplying by I doesn't change a matrix. Seems reasonable. All right, what else have we got? Definitions. All right, first definition. Given an n by n matrix, so we would call this a square matrix, A. We are going to define A to the K, and it is the product of K copies of A. And what I mean by that is it looks like an exponent, and it is treated like an exponent. A to the K equals A times A. I guess I should say that we're only going to be worried about this where K is an integer. K times. I'll say where K is greater than or equal to 1. K is an integer. So, for example, if you ever saw a problem that said a squared is just a times a. If you saw a cubed, it's a times a times a. And we could do those. We know how to do the matrix multiplication now, so you could do a times a. So that was the definition for a to the k. Yeah. I'm not going to underline it. It's just there. Another one. Another definition. Given an n by n matrix A, the trace of A denoted by trace parentheses A or TR of A is this one's pretty simple. The sum of its diagonal entries. I'll tell you that trace is relatively simple, but it actually has some interesting properties and applications. For right now, I'm just going to show you two quick little examples of trace. Let's say if A were equal to this 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the trace of A. So what do you think? It's supposed to be the sum of its diagonal entries. What do the diagonal entries mean? Remember, earlier we said that the diagonal entries are things like A11, A22, A33. It's the entries on this main diagonal. So it's going to be the sum of those, 1 plus 5 plus 9. So it's 15. That's it. I mean, what does that 15 represent? Well, maybe later in the course, we'll see some of those interesting properties or applications I was talking about. But for now, we're establishing some definitions. And the trace is the sum of the diagonals. I said there were going to be two little examples. Oh, the other one I wanted to show you is, what if we had the trace of the n by n identity matrix? What do you think that is? What do you think that equals? Isn't the n by n identity matrix look like this? There's ones all along the main diagonal. I guess if it's n by n and we want to be general, then we kind of don't know how big it is. Is it 3 by 3? Is it 10 by 10? Everywhere else there are zeros, right? Maybe I could indicate that by, how do you want to do this? We could say 0. We could say dot, 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 0, dot, 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 0. Something like that. It's all zeros except for the main diagonal. Let's circle the diagonal. So it would be 1 plus 1 plus... Seems like there are n of these. So you do 1 plus 1, do it n times, so you get n as the answer. So if it was the 3 by 3 identity, then the trace of it would be 3, and so on. That's just two little examples of trace. You could do some other examples. The trace of the 0 matrix. The trace of the n by n 0 matrix would be 0. All right, let's see. I think I had one more definition here. So under this heading of definition, so far we had a to the k, we had the trace of a matrix, and now one more is, if we're given an m by n matrix, A, the transpose of A denoted A with a capital T up there A with an uppercase T, it looks like an exponent, but it's not an exponent. Okay, it's a special notation that means this concept called transpose. It is the matrix obtained by interchanging rows and columns. And I'll show you what I mean by that. Example, if A equals, now in this definition, it doesn't say that A has to be a square matrix. So let's do an example where it's not square. So we're going to go 7, 8, 3, -1, 0, 5. Remember, in the definition of trace, it said the matrix had to be n by n. So for trace, you have to have something square. For transpose, you don't. Then, we would pronounce this as the transpose of A, or we sometimes pronounce this as A transpose. A transpose. How do we swap the rows and columns? Interchange just means you swap the rows and columns. So the first row of A is going to become the first column of A transpose. The second row of A is going to become the second column of A transpose. And that's it. Kind of like we rotated at 90 degrees, right? You took the matrix and you kind of, you rotated counterclockwise, I guess, 90 degrees. That's all. That's all there is to it. And it actually does turn out to have some interesting properties and some interesting applications. I think I am going to show you some of the properties of transpose right now. Here's an idea. What happens if you do the transpose of the transpose? What do you think happens? You take the matrix, rotate it like 90 degrees, and then you do the transpose again? Maybe rotate 90 degrees might not be the best. Maybe rotate 90 degrees might not be the best explanation. Maybe I should just stick with what I wrote. Interchange rows and columns. So you start with A, you interchange rows and columns. You get A transpose. What if I did transpose again? I would interchange rows and columns again. Here, let's write some of this down. This is going to be a property. So properties. I know I said rotate, but maybe I should just stick with interchange rows and columns. All right, part A. First property is this thing that I was kind of talking about. What if you do A transpose and then you do transpose again? Well, it's going to just equal A. Because what happens is the first time you do transpose, you swap the rows and columns. The second time you do transpose, you swap the rows and columns back. So they undo each other. You just get right back to where you started. How about this? A plus B transpose equals it actually equals A transpose plus B transpose. It actually is sort of distributive in that sense. I don't know if you find that surprising or not. I think maybe at first glance, when we've just learned what transpose means, I think maybe this does seem a little bit surprising, but it does work out. Property C is that if you have R is going to be a scalar. If you have RA transpose, where RA is in parentheses, that's the same as R times A transpose without parentheses. So you can either do RA and then do the transpose, or you can do A transpose and then multiply by R. This is for any scalar R. And I've got one more on this little list of properties. A, B, in parentheses, transpose. All right, now, this one is matrix multiplication. This kind of looks almost like property B above. I haven't finished this yet. We're gonna say what this equals. Okay. I'm saying that properties B and D start out similar, right? B is the sum of two matrices, transpose. D is the product of two matrices, transpose. Do you think this one is also going to be distributive? Do you think it's just going to be like A transpose, B transpose? Or do you think it's going to be something else? This one might be a little bit surprising. It actually equals B transpose, A transpose. Interesting, interesting. I think that's the most surprising out of these. So, in the textbook that we're following along with, the proof is an exercise in the textbook. It's problem 33. So you can try that on your own. See if you could try to prove that. It would be an interesting exercise. I think it's an interesting property. But yeah, it does work out. The transpose goes on both the A and the B, but the B and the A look like they kind of swapped places. Let's see, we're almost at the end. I have one more thing I'd like us to do. So what we just went through were 3 quick definitions. We had a definition for A to the K, a definition for trace, a definition for transpose. And then we had some properties of transpose. I want to tell you, be careful to not mix up trace and transpose. I know that they both start with TR. I know that we just talked about them side by side with each other. But remember, the trace is just the sum of the diagonal. The trace of a matrix is always equal to some number. You could say the trace of A equals 15, right? But the transpose of A is a matrix, not a number. Anyway, I want to give you a problem to try because we just had a bunch of definitions with no problems. So I'm going to give you A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm going to ask you to find A transpose minus A. All right, so take a minute, pause the video, and give that a try. Okay, this one's really not so bad, right? So I think A transpose minus A is going to equal, first of all, let's write A transpose. So every row of A becomes a column. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's A transpose. And then we want to do minus A, so I'm just going to copy A. So it's a matrix times a matrix minus a matrix. 3 by 3 minus 3 by 3. And now we just subtract the corresponding numbers. 1 minus 1 is 0. 4 minus 2 is 2. 7 minus 3 is 4. Next, we have 2 minus 4 is negative 2. 5 minus 5 is 0. 8 minus 6 is 2. 3 minus 7 is negative 4. And you get negative 2. And look at that. That's kind of an interesting looking answer, isn't it? All right, that's the answer. Pretty cool. Pretty cool. I don't know. I think it's interesting. I think the answer has like an interesting symmetry to it. we did A transpose minus A. Maybe this helps illustrate a couple of things. One thing that you can see is that here's A transpose. All right, let me just say this was A transpose. This was A. One thing that you could see is that both A transpose and A, if you're dealing with a square matrix, A transpose and A both have the same main diagonal, 1, 5, 9, 1, 5, 9. So when we subtracted, we got 0, 0, 0, because it was 159 minus 159. So that's kind of interesting. Some other stuff is interesting here, like the entry in the upper right is the negative of the entry in the lower left. Do you think that would always happen? Like if I gave you a different 3x3 matrix, would that always happen? It kind of looks like it would. I think we could say, you know, side note, looks like maybe we would say as a hypothesis, I notice that we got 0, 0, 0 as the diagonal, so it kind of looks like the trace of AT minus A is going to be 0 for any square matrix A. Maybe we could say that as a hypothesis and we could try to prove it. That's kind of an interesting little side note, an interesting little property, because that involves both trace and transpose in the same sentence. I don't know if you're like me or not. I find that interesting. But all right, so we're going to wrap up here. All right, so this lesson did actually wind up a little bit longer than I thought it was. I think I said at the beginning that this lesson was going to be a little bit on the lighter side, but it turned out that we actually did have a lot to cover. So some of the big things to take away from this are definitely matrix multiplication. I think that the row column rule, the way that we were doing matrix multiplication problems towards the end, I think that that's going to be useful throughout the course. And then we also had a bunch of other definitions, terminology, notation. You want to know about the diagonal entries. You want to know about, you know, the zero matrix, the identity matrix properties. And then, you know, some of the other things we talked about towards the end, like trace and transpose. Those might not come up quite as often, but at least we've established what they are so that when they do show up, it won't be a complete mystery. Okay, so that's going to be it for now. I will see you all next time, and take care.